So I get turned off. That's what bulking means. So before I can bulk, in the simulation, I had to specify the length of the queue wherein I would decide to bulk. So that's the relationship between that. Passengers changing vehicles at web. Not all the modes need to do this, need to consider this. If a mode of operation goes directly from end to end, then definitely not. But if it does, you have to consider if it changes vehicles at web. If I came from a station, am I the first transfer to the other vehicle? So it may be first in, first out method, or last in, first out. And then finally, I vary the system design parameters, which I already discussed earlier, for the simulation. Now, I come to the more exciting phase of the research, which is the discussion of the results. Now, what's the best system design parameters that I came up? Remember that I have 4 categories: class peak, off-peak, mealtime, special events. Now I'm discussing class peak. For class peak, there are 2 things that you have to remember. Class peak with original parking and class peak with infrastructure modification or additional parking at Powhatan. So what is the challenge here, or what is learned here, is that the procedure in determining the best system design parameter, specifically the best mode and the best capacity, the method that I use is, I have 11 modes. I have to narrow it down to just 1 mode. And the second step is to get the seat capacity from that best mode. Notice that this is unique for this situation. In other loading, like special event, this is not true. This is true for class B, because even if you have a lot of passengers coming, or the ridership demand is high, you still have the same mode, or the best mode still comes up the same. And you'll see it in the next, in the following chart. What do you see here? See, the x-axis is the capacity of the sled. The y-axis is the average total trip time per arrival in seconds. And I have simulated all 11 modes. You can see here the average walking speed, the red arrow. It's approximately 274 seconds. And so I simulated heavy demand, heaviest demand at the highest intention, meaning, highest intention, highest demand. That's why at 18 seat capacity, it's almost near to walking time. But the important thing is, the 3 best modes here are the double, asynchronous, synchronous, and elevated double. Now, by the way, that's for TED to Web station. For Powhatan to Web, same thing. X-axis is the seat capacity, Y is time in seconds, simulate all the modes. This is the average walking time. Now, as I said earlier, the mode of operation is, you can say, independent of the ridership demand. So, for Powhatan to Web, you have a lesser ridership demand, but still the 3 best modes come up. There's double, synchronous, asynchronous, and elevator double. I looked at the heavy demands for both station pairs. Now, the next 2 charts, this one, TED to Web, and Powhatan to Web, you can see, you can observe that the 3 best modes are still there. So, from the charts alone, 3 best modes, the 3 above. So I concluded that, from those 3 modes, I just have to pick one from them. And for me to do that, I have to consider other figures of merit, or other means of comparing it, aside from the average total trip time. This time I used the number of bulking passengers. So what you see here is the capacity and the number of passengers bulking, or getting turned off. So this double synchronous is slightly higher. It doesn't give much, certainly you can see some difference. And due to that, I decided, all right, from those figures, and other figures of merit were considered also. But I chose double elevator as the best mode. Why? Simply because if you're talking about class peak times, it happens, before a certain class. In the research, is 20 minutes prior to a class. Double elevator allows you that ability to transition seamlessly from one type of loading to another. You don't need any centralized person monitoring, hey, the ridership demand suddenly went up high. You have to change to another mode. You don't have to do that with double elevator mode. Because for double elevator, you just have, it depends on the number of passengers. You just press the button and it will automatically go. But if the ridership demand is high for double elevator mode, it functions as like the previous double asynchronous. So it will still be able to satisfy the ridership demand. Now, I know now my best mode, double elevator. So the next challenge is, what's the best capacity? How many seats do I need? So what you see here is, again, x-axis is the number of seats in multiples of 9, but it started from 18. Average total trip time in seconds. And this, all the loadings were simulated. All intention levels for each type of loading, heavy, moderate, and light. We're talking about average total trip time for arrival again. Just focus on heavy, which is the blue line on the left side of each cluster, and focus on the light green, which is the right-hand portion of each cluster. And what do we learn? What do I learn here is, and everything is that as the seat capacity increases, the average total trip time decreases to a point where it now settles to a total trip time which is almost steady state, or the lowest trip time possible. So that is what I'm trying to obtain for the best seat capacity. Where does it occur? Which seat capacity do you actually get the optimal trip time? So, by the way, that is for TED to Web. And I also look at the other station, Powhatan to Web. Same thing, seat capacity, trip time in seconds, simulate all the loadings, and heavy and low, you can see, blue and green, everything else in between. But the main difference is, if you look at TED to Web, the ridership demand is quite low for Powhatan to Web. That is why, even at 27 seat capacity, you already achieved the optimal seat capacity. So, summarizing everything, other figures of merit were also considered, not just that. But I want to focus your attention here. So, this chart shows, this upper box shows there are so many class peak demand. You can categorize it for the whole day as heavy, moderate, and light. This just shows you the number of passengers with corresponding intention levels, and just a method for ranking it. And the heavy, moderate, and light, you can see the optimal sizes chosen. So the vehicle size for a heavy demand class peak is 72 seats for TED to Web and 36 seats for Powhatan to Web. For moderate, it's, as you can see, 3618 and light 1818. Corresponding to optimal trip times, this is the optimal trip times possible. Corresponding to optimal bulkers, there's negligible, it's almost zero. But now